So my next question is, let's talk about point charges. We've talked about parallel plates. And so it turns out the formula for the electric field near a point charge is just kq over r. Remember, E, the electric field near a point charge, is kq over r squared. So it almost looks like it's just dividing by r again, just like for the parallel plates we were dividing by the distance. And it's not quite the same thing, but it sort of looks that way. So if I have a charge q here, right, I can say, suppose I have a distance of 2.0 meters. This is my point A. So what's the electric potential at point A if the charge is 4 microcoulombs, right? And so V is equal to KQ, I'll just do it lowercase, over R, which is 9 times 10 to the 9th Newton meter squared per coulomb squared times 4 times 10 to the minus 6 coulombs divided by 2 meters. So 4 divided by 2 is 2, times 9 is 18, so I have an 18 here, times 10 to the 9 times 10 to the minus 6 is 10 to the 3rd, so it's 18,000. So it's coulombs cancel, and one of the meters cancel, and I get Newton meters, which is joules, or 18,000 volts. So when we're talking about point charges, the electric field has this formula, which we've talked about already, and the electric potential has this formula. The electric potential, or the voltage, a distance r from a charge q1 is V equals kq1 over r. Notice the electric field is kq1 over r squared, right? This is the force per charge, this is the potential energy per charge, and so they look the same for a point charge, but they're not quite the same. And we could say, what is the electric potential 3 meters from a 2 microcoulomb charge? And we say, well, V is equal to KQ over R. I'll leave off the 1, and that's 9 times 10 to the 9th Newton meter squared per coulomb squared times 2 times 10 to the minus 6 coulombs, all divided by 3 meters. So if I just take care of my units, I get a coulomb, and one of these coulombs cancels, and this meter and one of these meters cancel. And so I get my units over here are Newton meters per coulomb, right? And 9 divided by 3 is 3. 3 times 2 is 6. So the non-exponential numbers, the non-10 numbers, give us 6. And 10 to the 9th times 10 to the minus 6 is 10 to the 3rd. Or V is equal to 6 times 10 to the 3rd joules per coulomb, which is 6,000 volts. And so a distance of 3 meters from a 2 microcoulomb charge, you're at 6,000 volts. Notice that in order for this quantity to be 0, R has to be infinity. And so V goes to 0 as R goes to infinity. Notice that if the charge is negative, then the voltage is less than 0. And so you can have a negative voltage or a positive voltage. If you remember, the electric potential is the potential energy per charge, And so that means the potential energy is equal to the charge times the electric potential. For point charges, this becomes Q, little q, times KQ over R. So I'm just picking, I can use Q1 and Q2 or big Q and little q. Hopefully you're not bothered by the different names. And so this is the charge whose electric potential we're talking about, and this is the charge we're bringing near. And so in our last example, we could say, from the last example, we could say, what is the potential energy right? We could say, what is the potential energy due to a charge of 0.5 coulombs, microcoulombs, placed 3 meters from a charge of 2 microcoulombs. So here's our 2 microcoulombs charge. This is our big Q equals 2 microcoulombs. And then over here I put a smaller charge, little q, equals 0.5 microcoulombs. It doesn't matter which one's bigger. And then this distance is 2 meters. And you can tell there's some potential energy here because these two guys repel each other. And if I let them go, they'll go flying apart, and they can do a bunch of work when they fly apart. And so they have potential energy stored. Well, this is the formula for the energy stored. So the potential energy is QV, but we just calculated V, right? We said V was 6,000 volts, so this is 0.5 microcoulombs times 6,000 volts, which is 0.5 times 10 to the minus 6 coulombs times 6,000. A volt is a joule per coulomb. And so if I straighten my units out, I cancel that, and I get joules. And then this becomes 0.5 times 10 to the minus 6 times 6,000 joules. Right, the coulombs cancel. 10 to the minus 6 times 10 to the third is 10 to the minus 3, and so this is 3 times 10 to the minus 3 joules. And so that's how much energy is stored there. I could have just used this formula and plugged back in the K, the Q, and the K, the big Q, and the R, and the little q, but we had already calculated this number in the previous video, and so I just used that one. And so anytime I want to know the potential energy between point charges, so KQQ over R, I've just switched the K and the Q. I can multiply or divide things in any order. Is the potential energy between point charges, little q and big Q, or any 2 point charges that are a distance r apart.